All right, in this explainer, we're going to get right to the heart of how AI actually learns. We're breaking down the three fundamental ways that power just about everything you see in machine learning today.
So let's kick things off with the big question that really frames everything we're about to talk about. When we talk about a machine learning, what does that actually mean? What are the core strategies it's using to get smarter from all that data we feed it?
When you zoom out, it really just boils down to three main ways. A machine can learn with a teacher, kind of like a student who gets an answer key. It can learn totally on its own just by digging through raw data to find patterns, or it can learn by doing, through trial and error, by interacting with its environment. So let's dig into that first one.
Okay, so that learning with a teacher idea. Well, that brings us to the most common approach you'll find out in the wild, supervised learning, and it is incredibly powerful.
Now, I know a lot of you are probably familiar with databases, so let's put it in terms that might feel a bit more concrete. Imagine you've got a classic database table. A new row comes in, say a new customer. How could you predict a value in one of the columns for that new person? That is exactly the kind of problem supervised learning was born to solve.
So what's really going on here? At its core, supervised learning is all about learning a mapping. You give the machine a giant data set of examples where you already know the correct answer. These are your input and output pairs. The machine's whole job is to figure out the hidden rule, the function, that connects those inputs to those outputs.
And here's how that database analogy lines up perfectly. What you call a table, in machine learning, we just call training data. Your columns are what we call features. Those are the different bits of information. And each row, which has both the features and that known answer, is what we call a labeled example. The machine just crunches through millions of these labeled examples to get good at predicting the answer for new, unlabeled ones.
And the things you can do with this, they're everywhere. It can read thousands of restaurant reviews to figure out if a new one is positive or negative. It can listen to a song and tell you if it's rock or jazz. It can look at a picture and say, yep, that's a cat. It can even do really complex stuff, like look at a photo of a street and estimate how far away every single pixel is from the camera.
Okay, so supervised learning is fantastic, right? But it has this one big dependency. You need that neatly labeled data, that answer key. So what happens when you don't have one? What if the data is just, well, a huge, unlabeled pile?
Let's jump back to our database example for a second. What if you just have a massive table of data, but there's no special answer column you're trying to figure out? What on earth can a machine learn from that? Well, this is where our second big idea comes into play. And that, right there, is the whole idea behind unsupervised learning. You take away the teacher, you get rid of the answer key, and the goal changes completely. Instead of predicting a specific answer, the model's job is to just explore the data and discover its own structure, its hidden patterns, its underlying organization, all by itself.
And this approach unlocks some really mind-bending stuff, especially with what we call generative models. By learning the deep structure of what makes a cat photo, a model can then create brand new, totally realistic images of cats that have never existed. By learning the patterns in thousands of books, it can write a new story from scratch. It can even intelligently fill in missing parts of a photo or finish your sentence for you, because it's learned the deep statistical rules of images and language.
All right, so we've seen how a machine can learn with a teacher, and how it can learn on its own. That leaves one more big idea, and this one is all about learning how to act.
Yeah, the first two methods are really about looking at a pile of data and understanding it. But what about situations that change, that are dynamic? How does a self-driving car learn to navigate traffic, or an AI learn to become a grandmaster at chess? That requires a totally different way of learning.
Well, that's where reinforcement learning comes in. Think of it like this. The model, or what we call an agent, learns by doing. It's placed in an environment, it tries different things, and it gets feedback. Positive feedback, a reward, tells it, good job, do more of that. Negative feedback, a penalty, tells it, nope, avoid that. It's basically trial and error, but on a massive, super fast scale.
And the whole thing runs on this constant feedback loop. It's actually pretty intuitive. First, the agent looks around and observes the state of the world. Where are all the pieces on the chessboard? Then, based on its current strategy, its policy, it chooses an action. It makes a move. And finally, it gets a reward or a penalty. Did that move get it closer to winning? It uses that feedback to update its strategy, and then it starts the loop all over again, getting a tiny bit smarter each and every time.
So, okay, we've got these three totally different ways of learning, right? Learning with a teacher, learning by yourself, and learning by doing. But
What if I told you there's one powerful piece of technology that's been like rocket fuel for all three of them?
So what is that common thread? What's the engine under the hood that's driving all these incredible breakthroughs we're seeing? Whether it's recognizing images, generating text, or playing games at a superhuman level.
The answer? It's deep neural networks. These incredibly complex, multi-layered models are the workhorses of modern AI, and they play a unique but absolutely critical role in all three of our paradigms. So this table breaks it down really nicely. You can see how that same core engine, the deep neural network, wears a different hat in each paradigm. In supervised learning, the network is the thing that learns that complicated mapping from input to output. In unsupervised learning, the network becomes a powerful generator. It's the artist that can create brand new data. And in reinforcement learning, the network acts as the agent's policy, or its brain, learning the complex strategy of what to do in any given situation.
And all of this power, it kind of leads to one last really important question. These models can create amazing art. They can write paragraphs that make perfect sense. They can beat the best humans at the hardest games. But do they actually understand any of it?
While the source material gives us a pretty clear and maybe a little sobering answer. When one of these models gives you an answer, it's not because it comprehends your question. It's because it has analyzed the statistical patterns in trillions of words and has calculated the most probable sequence of words to come next. It's a master of statistics, an incredible pattern matcher, but it's not a conscious mind. And that's a really critical distinction to remember.
So there you have it. That's our quick tour of the three big paradigms in machine learning. If this helped you connect the dots, maybe share it with a friend or a colleague who's also trying to make sense of all this.
And hey, don't forget to subscribe for more explainers just like this one. Thanks so much for tuning in.